1.1 vectors, we will look at exercise 12. We are told that Ali runs on a windless day at a speed across an open field of 6 kilometers per hour at a direction of 150 degrees. This is his velocity because we have the magnitude of velocity known as speed plus the direction. Furthermore, we are told that the wind blows with a constant velocity at 12 kilometers per hour at a direction of 270 degrees. The 12 kilometers per hour is just the speed, and the velocity is the whole of magnitude plus direction. So let's define these velocity vectors. We're going to let A be given with a magnitude of 6 kilometers per hour at a direction of 150 degrees, be Ali's velocity. And this is Ali's velocity with no wind. And we are going to let, let's use W for the wind's velocity, which is 12 kilometers per hour, acting at an angle of 270 degrees, be the wind's velocity. And so really the question in part A is asking to determine Ali's velocity when he's running with the wind. This is really asking us to find the resultant of A plus W. And so we can give this another name if we want. We can call it V. But we know that we cannot add the two vectors in polar form. So the first thing we have to do is convert the blue vector and the red vector each to rectangular form. And we do that using the magnitude times the cosine of the angle and the magnitude times the sine of the angle. So I'm going to use standard vector notation and have 6 times the cosine of 150 degrees I hat plus 6 times the sine of 150 degrees j hat added to 12 times the cosine of 270 degrees I hat plus 12 times the sine of 270 degrees j hat. And right away, I know that the cosine of 270 degrees is 0, and so I don't have a vertical, or rather a horizontal component of the wind's velocity alone. So a simplification here requires us to simplify the trigonometry. The cosine of 150 degrees is the same as negative cosine 30 degrees. And if we use a 30-degree reference triangle, we see that the adjacent is square root 3, and the hypotenuse is 2, and when the opposite is 1. So the cosine of 150 degrees is going to be negative square root of 3 over 2, multiplied by 6 gives us negative 3 square root 3, number of I hats. The sine of 150 degrees is a positive 1/2, times 6 will be 3 j hat. Then just for clarity, we have plus 0 I hat from the wind, and 270 degrees points straight down, the sine of which is negative 1 times 12 gives us negative 12 j hat. So we can combine all of these according to like terms, and the total number of I hats is negative 3 root 3 I hat, and the total number of j hats is negative 9. The question then says to determine Ali's velocity, and it doesn't specify which form. This is a velocity vector, and it's the resultant, so we're done in part A. However, part B and C ask us really to be more specific about those components. In part B, we're asking how many degrees off his original course of 150 degrees does Ali run with the wind. So this is really asking us to dig deeper into this vector format in rectangular form to give us the angle of the polar form. And then in part C, we are asked to determine Ali's net speed. Knowing that speed is the magnitude of velocity, we are asked in part C to come up with the magnitude of the resultant vector. So the wording of this question in part B is asking us to come up with the direction, or really a difference between the net resultant direction and the original direction that Ali wanted to run in. And part C is asking us to come up with the magnitude of the vector. So I'm going to pause the vector, give you a chance to work those out yourself, and then compare with my answers. In part B, we are working out the direction of the resultant vector. So we first get the reference angle measured from the net vector v to the nearest x-axis. So this is the reference angle that we are working out here. And we get tan inverse of the absolute value of delta y over delta x, which gives us 60 degrees. So this red angle is 60 degrees. That means that the actual green vector has an angle of 180 plus 60 degrees, which is 240 degrees. And therefore, the change in the angle from Ali's intended course and his actual course with the wind is a delta theta, which is 240 minus 150, which is 90 degrees. So the wind in this example is pushing Ali 90 degrees off the course or the direction that he intended to travel, to run. In part C, we are coming up with the net speed, and so we use Pythagorean Theorem. The net speed is going to be 6 times the square root of 3, and you can see that I've done some maybe unusual factoring here. I find it helpful for simplifying the radical. After I square both terms, I can keep the negative 9 squared or the 81 in factored form, and I can see a common factor of 9. When I factor out that 9, I'm left with 3 plus 9, which gives me 12. So I have 9 times 12, and then I further factor the 12 into 4 times 3, and from all of these perfect squares, I can simplify the 3 from the 9, a 2 from the 4, giving me the 6 outside, and the square root of 3 inside. Now I know that this number 6 square root 3 is greater than 6, so I know that with the wind, Ali is running faster than he does without the wind.